I am Anuradha Mathur. I teach physics at Modern School Vasant Vihar in New Delhi. We have been considering work, power and energy. In the last unit, we considered the definition of work, learned how to calculate it, saw that if the value of force changed, the value of work would also change. In this unit, we are going to consider the work calculation if the force is constant and if the force is changing, that means it is variable, it changes with time. We are going to learn how to draw graphs and how they may be useful. Then we will also try and do some simple real life example that might interest you. So, let us start with force being constant and try and recall from our previous lesson our equation of work as the dot product of force and displacement, and we are saying that the force is constant. As we said, it could be constant or variable. So, we will first draw the graph for constant force. This is my x axis and I will put displacement on it. The y axis is here and I will put force on it and apply my constant force, and it will be shown in this manner. Notice this graph is not competent to tell us about the angle between the force and the displacement. We are not even looking at that. Whatever be my value of theta, I can put for a constant force a graph like this. How does this help? Because the area under this graph for a certain displacement will give me the work done by the force in doing that displacement. Let us see, say from this location the displacement considers this up to this point, say this is some position S1. So, the graph area that is in question is this segment. Notice we just need to find F into S and we get the value for work. If the displacement was up till here, I would have to consider this additional section to calculate the total value of work. That is quite easy to understand. Now, let us see if a graph can help us calculate the work done in case the force is variable. You can have a choice of force which is steadily increasing, steadily decreasing, that means uniform increase or uniform decrease, or you could have it just changing any which way it wants. So, let us see the graph for constantly increasing force. On my x axis, as we have said, we will have the displacement, and on the y axis we have got the force. Now, this force starts from, let us say, a 0 value and increases to a certain value corresponding to say F1, and as a consequence of the force applied, say the displacement is up to a location S1. Now, the same rule applies, the area under the curve. The area under the curve in this particular case would be given as the area of the triangle, which would be half base into height. So, what would it be? Half S1 into F1, this would be the area, and if we were to figure it out in terms of the average force that is applied, what would be the average force? The initial force is equal to 0 and it gets to the value F1. So, the average will be the sum of these two extreme values and divided by 2. So, this is the average force. So, the work done as per our definition would be the average force multiplied by the displacement, and it would work out to be F1 by 2 into S, which is the same as this one. That means, the area under the curve is again giving us the value for the work. Let us consider a variable force which is not uniformly increasing, but just changing. These are very common in real life, and this is basically how it happens. So, this is the displacement and this is the force axis, but the force starting from 0 becomes more, less, like that. So, how do we now calculate the work done? If we have to follow the earlier condition, that just find the area under the curve, that is the simplest, which means that if I have to consider from displacement F1 location to displacement S2, then the area in question is this. You can either make small rectangles over here of very small displacement size and calculate the area for each of these strips, add them all up, or simply use integration. If you were to use integration, you should know the variation of this force with the displacement, and you will be able to find the value for work done by simply finding the area under the curve, which is also going to be the integrated value. We are going to take two very interesting examples. One is of a woman or a person who is pushing a trunk on a rough railway platform. So, let us see, we can give it some values and try and see if we can use a graph to calculate it faster and quicker. Here is the question. A person is pushing a trunk on a rough railway platform. He or she applies a force of 100 newtons over a distance of 10 meters. Thereafter, the person gets tired and applies a force which is steadily reducing to a value of 50 newtons. The total distance moved by the person is 20 meters. That means, our trunk moves 20 meters and the force of friction is 50 newtons. We are required to calculate the work done by the two forces. Which are the two forces? The force that the person is applying as push and the force of friction, which is trying to resist this motion. So, we set out to draw a graph. What kind of a graph will we get? According to the question, if we see, the total displacement is given to us as 20. For the first 10 meters, the force is constant and that constant value of force applied by the person is 100 Newton, and in the next 10 meters, for the next 10 meters, this force reduces to 50, which is half of the earlier value, but this time it reduces steadily, that means uniformly, and the force of friction is constant and its value is 50 newtons, and it is acting opposite to the displacement. So, I will show it by a dotted line like this. Notice I have put this value of friction below this line. That means, this is the force in the direction of displacement and this is the force in the direction opposite to the displacement. So, here is the friction force and here is the force due to the push by the person. So, the trunk has travelled a distance of 20 meters. This is the 20 meter mark, and let us see how we calculate now. So, the work done by the person is going to be the area under this curve, which is going to be just this rectangle plus the area of this trapezium. So, for us it will work out to be 100 into 10, which is the area of this section. For the next section, which is a trapezium, it would be half into the sum of the parallel sides, which in our case is 100 plus 50 multiplied by 10. On calculating this, it works out 1000 plus this value over here, this is 150. So, 1500 by 2, or the total value is 1750 and the unit will be joule. What is the work done by the force of friction? The force of friction is in the opposite direction, this was same. So, the value is simply this. Now, the area under this section is going to be, let us show it by a different way. So, the friction is going to give the work in this manner, and what will be the value for the force and the value for work because of that? I will write it here for you, and that is equal to minus 50 Newton into the same displacement, which is going to be minus 1000 joules. So, the push is there and the work done by friction is so much. Where have we lost all this work? This should be equal, but it is not. For one thing, we have actually displaced the trunk, and for the second thing, some energy must have been lost. Maybe the trunk produced sound, maybe because of the rubbing there was some heat produced. Some energy must have been lost. Some wastage is there, but this is how you can easily calculate by using a graph. We know that constant force causes constant acceleration in a body. If it is continuing to move, this constant force accelerates, that means causes a change in speed. If it is in motion in one dimension, it is very easy to understand. If it is a body which is moving in a circle, this constant force is only changing its direction and actually doing no work according to our definitions. So, we are considering a body moving along a straight path and a constant force acting on it, as a result of which we will have a constant acceleration on it. Now, when we see a problem like this, if there is constant force, the displacement per second is not the same. So, are we saying that the work done per second is not the same? Let us take a look at this. Let us connect first our equation, which will give us the value for acceleration. This acceleration is force divided by the mass of the body, and if the force is constant, the acceleration is constant, so long as the mass of the body is not changing. The displacement can be given by an equation which will suggest the acceleration acting on it for different timings. So, if a body is starting from rest, that means we take u to be equal to 0. At the end of time 1 second, this value is going to be a displacement of a t square. Now, let us give some value to the force and mass and acceleration. If a force of 1 Newton is acting on a body of 1 kg mass, we know that the acceleration is 1 meter per second square. Using this, our S1 value becomes half meter, S2 value will be half, acceleration remains the same, and our time becomes 2 square or becomes 4, or you will have a value of 2 meters. Notice, first you travelled only half meter, next you travelled 2 meters, and in the next second your travel is going to be half, 1 and 3 square, that is going to give you a value of 4.5 meters. Very interesting, because the force is constant, the displacement per second is not the same. So, constant force is not doing constant work on that body every second. That means, you could either do it by a graph, you can plot a graph and find the total work done, or just simply calculate at the end of so much time how much work is done, in which case you just need the application of these equations and therefore, work out the total distance travelled and the force that you have, which is already there. Product of these two will give you the total work, but not the work done from the first second to the second, from the second second to the third, or from the third to the fourth, and so on. Interestingly, this change in the rate of doing work needs to be described very, very often. For example, if you were to climb a set of stairs, the total displacement from the base of the stairs to the top remains the same. Let us see how. Here is a stairway, and if you were going from here climbing these stairs, the total displacement from the ground level to the top is h, whether you run up the stairs or you go slowly. So, the rate of doing work becomes a very important quantity, and this quantity we describe as power, and we talk of it as rate of doing work. And how do we calculate that? It will be just work done divided by the time taken to do so. What will be the unit for power? Unit for power would be unit of work divided by unit of time, that is joule per second. This is often called watt. What will be the dimensions for it? Dimensions of work, which is m L square T minus 2, and divide that by dimensions of time, and you are going to get the dimension for power as m L square T minus 3. This concludes our looking at two simple examples in real life and seeing how graph can be used to calculate the value for work. We have also seen that constant force does not mean that the work is going to be constant throughout the journey of a body. In fact, the rate of doing work continuously increases, and so we needed the term power, which describes the rate of doing work, and we have just seen that it should have a special unit and it should have new dimensions.